Good morning, Boston. Wow, what a great turnout of AI practitioners in this room. My name is Smitha Shyam, and I lead the simulation org at Waymo. We build the technology that is used to evaluate and improve the Waymo Driver, which is what we call a fully autonomous driving system. We recreate the physical world, all the static dynamic elements, so that we can run the Waymo Driver in this virtual world and have the confidence before we ship the Waymo Driver onto the roads. But before I begin my presentation, I need you all to make a very important decision. Are you all ready? Matrix style. Do you remember the red pill and the blue pill? So you can choose to take the red pill and remain grounded in reality, or you could choose the blue pill and join me on a journey into the dynamic simulated worlds. In the movie, Neo chose the red pill. What should we do? Based on some of the nods I see in the room, for this presentation, we are going to be blue pill all the way. So like the Matrix, the Matrix is a good analogy for what my team does. Just a lot less kung fu, a lot more math. Like Neo, we build worlds that are very similar to the real ones. While they use the virtual world to bend reality, we use the virtual world to make it ready for reality. At Waymo, every virtual mile that we drive helps us discover the unpredictable, so that every real mile driven by the Waymo Driver becomes a lot safer, becomes a lot smarter. And that's how the Waymo Driver, which started as a technological wonder, has turned into something even more valuable, a consistent, trusted experience relied by our riders every single day. Now, rather than take my word for it, let's hear directly from our riders.
Hey, what are we doing?
We're in our first ever Waymo.
And what does it mean when we're in a Waymo?
It means that there is nobody
Nobody driving this thing!
And this is a fully autonomous Waymo ride.
I cannot believe this. The car did a better job than if somebody was driving.
The truck was over the yellow line, so the Waymo braked and moved to the side.
It knew how to pronounce my name.
Oh my God.
Oh, it's nice. I love it. This is good.
This is so cool.
I'll never forget this. Never.
All right. So besides being a fun ride, the Waymo is urgently needed. Unfortunately, every year, more than 1 million people die in traffic accidents. And most of this is due to human error. This number that you see is staggering, and the status quo is simply not okay. We must do better. And that's why, 15 years ago, we started off as a Google project before spinning 8 years ago into our own company, Waymo, with the lofty mission of being the world's most trusted driver. And in this presentation, I'm going to walk you through how we use AI to accomplish that mission. So the scale that we're talking is large. The Waymo Driver has already logged more than 100 million miles in driverless mode on public roads. Paying customers can call a Waymo in 5 major US cities: San Francisco, LA, Phoenix, Atlanta, and Austin. And we are expanding to even more cities, as you can see on this map. We are going to New York, we are going to London, and also cities that are affected by snow. So this scale is huge, but it's not daunting because we believe we have the right approach in building this product. Make no mistake, the problem, the AI problem that we're solving is very challenging. Our AI runs in the car in the physical world. And we have 3 broad buckets of challenges. Number 1, the real world is complex, it's unpredictable, and it's downright messy. Second, ours is a safety critical problem. The cost of a mistake is really high. And finally, unlike Gen AI that runs in the cloud, we don't have seconds to make complex driving decisions. Our embodied AI has to make these decisions in real time in a matter of milliseconds. So here are some examples of the messiness out there, and we have seen it all. Stray cyclists, debris falling off of trucks, toddlers on the loose on the road, falling trees, distracted drivers, you name it. So most of driving is boring, but at the scale at which we operate, even the extraordinary becomes ordinary. So how do we deal with all of this? With powerful sensors and state-of-art AI. Our cars are equipped with sensors of multiple modalities. We have cameras that give us semantics. We have LiDAR that gives us 3D, and we have radars that helps us do object detection, velocity, and inclement weather. Our current generation Waymos have 29 cameras, 5 LiDARs, 6 radars, and 4 audio receivers. And together, they give us a range of about 500 meters and helps us see day or night and in all sorts of weather. So here, you see this scene play out at night. So 2 dogs are chasing a ball, crossing the street, and 2 humans running after the dog. The Waymo detects it in time and brakes for them. What you see above is how our LiDARs and radars are perceiving the system, and what you see below is how our cameras are picking up the scene. So in addition to powerful sensors, we also need great software. And a lot of people think that you need to build a driver with state-of-art AI, throw in lots of training data, and that's it. After all, isn't that what the bitter lesson of AI is about? So yes, you do need a good AI driver, but you need so much more. You need a good simulator to be able to test the driver for challenging situations. You need to have a good critique to evaluate the driver behavior. And you need to have a way to tell if your driver is ready for full autonomy. So to scale, you need to have solved each of these problems really well. And I'm going to walk you through how we use AI to solve each of these challenges. So most of you are familiar with vision language models. So VLMs, they are trained on broad world, on all of the world's internet data, and they have broad world knowledge. They are multimodal in the sense that they take audio, video, text, images as input. Frontier VLMs today have really good chain of thought reasoning, and they're flexible. They can be adapted to a number of tasks. So we have been playing with VLMs for a while now to understand the ability and to adapt them for self-driving. So let's take this example. So let's say it's Wednesday, 4 p.m., and we have to park in front of this parking sign that you see. And it takes a while for a human to reason, but VLMs can do a good job. They can give you an answer. They can reason through these parking signs and give you an answer very quickly. However, the question is, can we use these VLMs for the task of self-driving itself? Not straight out of the box, because they lack some core capabilities. These VLMs, they cannot adapt, or they cannot handle all of the sensor inputs, and we have LiDAR and radar, and convert them into action sequences that needs to be executed by the car. And they certainly cannot do this in real time. So we need to do a lot of work to adapt these VLMs to be able to handle the complex driving scenarios. And the first thing we are doing is just that. We are building a foundation model that will help us solve each of the 3 challenges I described earlier: being a good driver, being a good simulator, and being a good critique. And we call our foundation model, obviously, the Waymo foundation model, and it's an encoder-decoder architecture. It starts with the sensor fusion network. This is our encoder model. So this fuses the information across all of the sensors and across time. Now, the tokenized embeddings that this encoder model produces is consumed or decoded by the action decoder, which produces the action sequences for the AV. It also produces behavior predictions for other users and some other predictions. Now, these two models have some world knowledge, but not all the world knowledge like the VLMs, and they certainly cannot reason. That's why we are adding a driving VLM that can analyze complex scenes and reason about the higher level actions that the driver needs to take. So let me give an example here. Let's say our car is stranded behind a stationary vehicle with the blinkers on. So the car can reason that this vehicle in front of us is not going to move and maneuver around that vehicle. So the tokens from the driving VLM along with the sensor tokens improve the overall predictions of the Waymo Foundation model. You can think of it as think slow and think fast capability working simultaneously. All right, so the Waymo Foundation model serves as a versatile, flexible base on which a tech stack is built. From this, we adapt the teachers for each of the tasks. Now, the teachers are powerful, and they cannot be deployed to the car or even run in the cloud to simulate the millions of miles that we need. So we distill these teachers into practical-sized students that meets our real-time needs and a compute envelope. So this is sort of a 30,000 feet view of how we leverage AI in self-driving. I'm going to go deeper into the simulation pillar next. All right, so what happens if we don't have a simulator? Then the only way for us to test an AV would be on the road with the safety driver or do closed course testing. Now, with each of these methods, it's very slow. It takes months or sometimes even years to get all the data we want. It's super expensive, and there are safety risks. And in spite of doing all of this, there's still coverage gaps because certain scenarios cannot even be run, maybe because of weather, because of high speeds involved. And they're certainly not repeatable over the thousands of software and hardware upgrades that we need to do. And that's why we need a simulator that can help us replay logs, and I'll continue talking. That's why we need a simulator that will help us replay the logs as well as create the diverse scenarios in order to train and evaluate the AV. We'll wait for the simulation modeling ecosystem to come up. All right, thank you, Bruce. So picking this back, the simulation teacher is adapted from the Waymo Foundation model. The task for the simulation teacher is to predict the next frame. It is fine-tuned using Waymo logs, and it is post-trained using closed-loop training and reinforcement learning. We derive the simulation student from the simulation teacher, and the simulation student is used to generate semantic scaffolds, the what and the where of the world. The simulation student then conditions a generative video ecosystem that generates the high fidelity sensor data, the how does the world look, the sensor skin. So a few years ago, we were either able to just replay the logs on the simulator or entirely create from scratch these synthetic scenarios using a lot of human input and render it through a game engine. But today, because of the leap in Gen AI, we are able to realistically vary any part of the log or create entirely novel scenes with very minimal human input. So you want to see this powerful simulation in action? Let's go. All right. So here you see two scenes of a typical street in San Francisco. Can you tell me which is real, which is generated? Who thinks the left-hand side is generated? Raise your hand. Very few hands up in this room that think the left-hand side is generated. In fact, it is generated. So we have conditioned the vehicles and the road graph, but everything else in that scene is a generation. Pay close attention to the pavement coloring, the maturity of the trees that you see in the back, the buildings. There's a lot of detail that's packed in this simulation to make it mirror reality. What you see on the right-hand side is what we have collected from the logs, from the roads. So generation is one thing, but controllability is another requirement. So here's another example of, this is multi-view camera rendering. Again, I think this is San Francisco. So our system can programmatically insert vehicles or remove vehicles from a scene. We can do something similar even for pedestrians. So this enables us to simulate different traffic conditions and behaviors of other users. And then it helps us evaluate our Waymo driver. We can even change the scene to be snowy or change the time of day. Now with the Boston winter around the corner, maybe we should talk about weather. So what you see on the right, left-hand side there is a logged segment. And on the right, we have swapped the scene to be snowy. Again, the vehicle is conditioned, the road graph is conditioned, everything else is a generation. So we can vary these driving conditions. Again, that helps us to evaluate the AV, and we can do that across a number of scenarios. So here you see that we've taken the same scene, added dust into it, changed it to rain, snow, added some sun glare to test our sensors, and then some fog. So in addition to the camera viewpoints, we can also generate the LiDAR viewpoints. And what you see below each of those GIFs are the LiDAR viewpoints. So what's really valuable for us is to be able to create the dangerous conditions that could lead to accidents, like having to drive through fog or heavy rains, or the long, long tail, like let's say a forest fire in the night, or a Boston-style snow on the Golden Gate Bridge, which has never happened since 1976, I believe. So these visuals give you an idea of the role AI-driven simulation plays in helping Waymo scale safely. I want to go back to our pillars of autonomy chart. So we need a driver, we need a simulator, we need a critique to scale autonomy. But we also need a way to tell if we are ready for full autonomy. And that's where our readiness and safety framework comes in. Waymo, over the years, has developed a comprehensive safety and readiness framework that we use. So every update, every software update to the Waymo driver goes through this process to quantify its readiness. And that's how we've been able to scale the Waymo driver. It routinely does more than 250,000 weekly paid trips now. So the Waymo is popular. But the question is, how does it do against its mission of being the world's most trusted driver? Remarkably well. Over the 100 million miles that the Waymo has navigated, and I think the study was done at 96 million miles, the data shows that across a number of safety matrices, the Waymo is safer compared to an average human driver. We also regularly release insights into our safety framework so that the community develops a deeper understanding about this space, as well as it serves as a guide to others in the industry. Now, all of this is stats. Maybe let's turn it into some action. Here's a scene recorded by the Waymo Driver in Austin. This is nighttime, and you see a vulnerable road user, that's the person on the scooter, who loses control and falls on the street. The Waymo detects it, and in a split second, maneuvers around the scooter user while maintaining a safe distance from other road users. Let's see it one more time. Here's another scene. This is a busy street in San Francisco. The bus is blocking half the intersection. The light turns green for us, and we proceed. But then we detect a pedestrian on the other side of the bus who is not visible to the human eye, and then slow down. Our sensors picked up the movement of feet from under the bus, and this sparse signal was enough for the Waymo Driver to detect that it's a pedestrian, predict their next move, and then defensively take action much earlier than a human driver would. So these videos, these stats, are a powerful reminder of what's at stake for embodied AI on our public roads. It's people, it's lives. And our holistic approach enables us to build high-performing systems that work in real time to navigate these complex driving situations. And we can only get this performance by mixing the red pill of reality with the blue pill of simulation. And I'm happy to play my part in helping Waymo scale and make our public roads safer. So we are always hiring. Thank you so much for listening to this presentation.
Thank you, thank you. That was well presented. I think I know now why they don't have Waymos in Boston yet, because of those road signs that you presented. We don't have very clear signs at all. So we have some time for Q&A. Anyone have some questions that you'd like to ask? I'll walk the microphone around. You're the first one to put your hand up.
Hi, thank you for the great presentation. So I have a question around the edge cases that you showed.
Yeah.
So, for example, the person on the scooter, they lost balance and they came this way. What if there was a car behind? Do you run such edge cases in simulation with different scenarios?
Yeah, absolutely, we do that. So we create entirely novel scenarios in simulation, but we also take these interesting scenes that happen on the road and vary aspects of the scene, make it more harder, right? And we can do a number of those variations. And then in simulation, we can see the various outcomes. And that's precisely the advantage or the role of the simulator, right? Once you have that, then you can really alter what's happening in the real world and try it out.
Next question over here.
Hi, Smitha. This is Axel from CloudX. Smitha, one question is, you mentioned that you are using several sensors.
Yeah.
Are you using information from satellites? I understand that you're using real time, to make quick decisions. But in a Waymo, I saw that you were showing information in the screen, far from the car. So I was wondering if you're using information from satellites or...
No, we don't.
Only from the car?
Yeah.
Thank you.
Thank you, thank you. Next question. Got one right here.
So I have a question. Boston, Bangalore, and Brisbane are different.
Yes.
All starts with B.
Yes.
How do you, when you expand internationally, do you pre-train it on synthetic data? And how do you do that? Because, American cities, right now you're in American cities, they all look similar. It's same system of road signs, same stuff, but in Brisbane, they drive on the other side of the road.
Left-hand
side. How do you generalize?
Yeah, it's a good question, and that's where the generalizability of the AI driver comes into play. So first of all, you made a statement that most of the US cities are similar. They're actually pretty different. Take the example of traffic lights. Traffic lights in Austin are horizontal versus how they are in some of the other cities. So we've trained the Waymo Driver over lots of data, and it's fairly generalizable. And we continue to add to this training set. It's a mix of real-world data. We also use synthetic data. So it's a combination of these data sources and the AI architecture that we have. Yeah. But yes, in the sense that because we have the simulator, we can change right-hand driving into left-hand driving, and then use the millions of miles, information from the miles that we already have to ensure that those don't occur on these newer cities.
All right, Smitha, we have our last question here.
Hi, Smitha. By the way, great presentation. I have a question more on the electromechanical side a little bit. So I've worked in sort of adaptive cars myself, and one of the things I've noticed is that the braking mechanisms, damping mechanisms, and all these things were sort of designed sort of for human usage. And when you sort of start to apply sort of adaptive mechanisms to those cars, I've noticed that the brakes wear out a little bit faster. There are other issues that sort of start to arise at the mechanical level that could cause problems. How have you handled those sort of situations? Because you're sort of retrofitting the car, but you haven't designed the car for autonomous driving. It's sort of gone the other way around.
No, so we actually designed our cars for autonomous driving. And I think let me zoom out from your question. I think your question is, in some way, what happens if there are failures in the car, right? The car
was designed for a human driver, right?
No.
The damping mechanisms, the braking mechanisms, all the way you sort of apply the brakes was sort of for a human.
So our car is designed for AV, and then we have fallbacks for each of these things, right? For our sensors, for various aspects of the hardware, there is fallback. So that way, the car can rely on these fallbacks and get to safety. Yeah, because that's paramount. Because everything that drives our decisions is safety. Like our mission is safety. Safety is paramount. And that's there in how we design our software. That's there in how we design our hardware.
Great. Let's give it up for Smitha.